Hello, everybody. So we're looking at 9.5 factoring binomials, part one. All right. This is the first section where we're getting into what is called factoring. We're going to be factoring our polynomials starting with a binomial. All right. So first things first, just get this simple definition of what factors are and this first simple example, and then we'll get into it. Okay, so first thing, what are factors? Well, we've seen factors previously in this class. I guess just a simple way. This is not a formal definition. This is just kind of my definition. Factors are numbers you can multiply together to get another number. All right. So if you guys remember when we were dealing with radicals, we would break them down into their prime factors. Okay, and those numbers, they're considered factors because they can be multiplied together to get that original number. So our first example here, if I were to find some factors of 6, they would be a 2 and a 3 because those two numbers multiply together to get that number. All right, so yeah, that's a really simple way of just thinking about factors. All right, today we're not just factoring a simple number like 6, we're going to be factoring a binomial, all right, which remember is a polynomial with two terms, all right? And but the way we go about doing it, at least initially, is going to actually be using these factor trees that we used in the past, though it's going to be different than the whole radical, thing. All right, so let's just get into it. Okay, so first things first is understanding, what is a common factor, and then we'll use that idea to factor this binomial. So go ahead and get this slide. Okay, so a common factor is basically numbers and variables that each term has in common. All right, so if I'm looking at these two terms, a common factor would be numbers and variables that I can take out of both of these terms that they both have in common with one another. Okay, well, right now, because we're sort of new at this, the easiest way to do it is to break these two terms down into their factors and then literally just see what they have in common. All right, so let's do it. So breaking down a 6, I know, again, we can break that down into a 2 and a 3, 2 times 3. All right, by the way, these are prime. They wouldn't break down anymore, so we'll leave it there. And then we also have this x. Okay, so what we're doing is very similar to what we did with radicals, but here's the thing. I like to put a little line in between it. And then let's break these down. I'll kind of explain what's going on here. So a 9 we know is, a 3 times 3. Okay, again, these can't be broken down anymore. An x squared is 2x's. Okay, so if we're looking for a common factor that these two terms have, we literally, since we've broken it down, it's sitting in front of us. We're looking for numbers and variables that they both have. Okay, so I notice both of these terms have a 3. Okay, as far as numbers are concerned, that's all they have in common is just, that single 3. Okay, as far as variables are concerned, it looks like they have a single x in common. Okay, so that is the common factor. It looks like these both have a 3x in common. Okay, what we do is after we figure out what that common factor is, the way I think of it is that we're taking a 3x out of both of these terms. We're factoring it out of both of them. We need to write what's left over after we take a 3x out of both of the terms. Okay, and the way we show that is in parentheses. We need to show what's left of the 6x and then what's left of the 9x squared. This plus sign is going to stay in the center. Sometimes I like to write that first. Okay, but if we take a 3x out of a 6x, what are we left with? Well, it looks like we're left with a 2. Okay, and if we take a 3x out of a 9x squared, what are we left with? Well, it looks like we're left with a 3x. Okay, and there it is. We factored that binomial. All right, and this would be our answer as far as if they asked us to factor it. Okay, I just want to kind of point out, eventually doing this process might not need, we might not need to break things down like this. You might be able to just look at the two terms and think, oh, it looks like I can take a 3 out of a 6 and a 3 out of a 9, and I can take an x out of this one and an x out of that one. I can take a 3x out of these two terms. Okay, well, then what's left over if I do that? Eventually, we might be able to do this in our head. But what I just showed you is kind of the surefire way of doing these problems. All right, so breaking them down with the factor trees, seeing what they have in common. That's the easiest way, maybe the easiest way of doing these problems. Okay, so yeah, let's just kind of make some sense out of this. If you guys notice, okay, when we factored, and this is using the same stuff, factoring is really breaking up polynomials, or another way of thinking of it, it's just the reverse of multiplying the polynomials. All right, you don't necessarily need to copy this slide, though. It wouldn't be a terrible idea. But what I want to show you is that normally in the past, we had problems like this. Okay, and they would ask us to multiply together. You know, we would distribute the 3x and we would get this 6x plus 9x squared. Okay, what we're doing when we're factoring is we're starting here and we're going in reverse. We're breaking apart the polynomial. Okay, so it's literally the reverse of multiplication, which is a little weird, but that technically is what's going on here. So I just wanted you to kind of realize that we're starting here now and we're breaking things apart. Okay. All right, so with that, let's try it with another one. Let's go ahead and factor out the common factor of this binomial. Go ahead and get this example. We'll do this one together. Okay, so right now, it might be difficult to tell what they have in common. So again, let's break them down first, and then we'll be fairly short. Okay, so a 4, I know that breaks down into a 2 times 2. X to the power of 4, I know is 4 x's. So I'm just breaking this thing all the way down. Okay, I draw this line in between just to show that it's not like when we are doing radicals, we're not pairing things up. We're seeing what they have in common. So it is different. That's why I like to draw that line there to kind of show, okay, this is all of its own stuff and this is all its own stuff. Okay, but 24, breaking that down. Remember, there's multiple ways you can break things down. The first thing I think of is 2 times 12. And then 12, I think of 2 times 6, cross it out. And then the 6, 2 times 3, cross it out. Okay, so there's all its prime factors. X cubed is 3x's. Okay, so now let's figure out what they have in common. What is the common factor of these two terms? It looks like they both have a 2, and it looks like they both have another 2. Okay, as far as numbers are concerned, that's all they have in common. Okay, as far as variables are concerned, it looks like they both have 3 x's in common, right? So let's just kind of circle them all together. Okay, and there it is. That's the common factors. That's what we're going to take out of both of these terms. Okay, so we're going to take out that 2. We're going to take out that other 2. And we're going to take out those 3 x's, which is an x cubed. Okay, what's left over goes inside the parentheses. Remember, there's 2 things here that we need to show as, as having stuff left over. I'm going to put that plus sign. So the first question is what's left over of a 4x to the power of 4 if we take out a 4x cubed? Well, it's sitting here right in front of us, right? It looks like there's just this x left over. Okay, what's left of a 24x cubed if we take out a 4x cubed? Well, again, it's sitting right here in front of us. It's this 2 and this 3, which again, I guess by the way, would multiply to get a 6. So let's just go ahead and show that that would give us a 6. Okay, which by the way, I could have done out here as well. I could have just shown that there's a 4 left over here. Okay, but I didn't want to skip too many steps. So let's just go one more step. Let's actually multiply that together. And let's show that we have a 4x cubed coming out. And what's left inside is an x plus 6. Okay, and there it is. We factored the binomial. Okay, here's the nice thing about factoring binomials. You can check very easily to see if you have factored it correctly. Okay, the way to check it is just multiply your your common factor back in and see if it actually gives you your original binomial. Okay, so let's just ask that question in our head. Is a 4x cubed times x a 4x to the power of 4? Yeah, okay, so that works. Is a 4x cubed times 6 a 24x cubed? Yeah, it is. Okay, so I know this is factored correctly. Okay, all right, cool. So let's try one more of these. I'm trying to think. On this next one, let's try to factor this next one in our head. All right, before we get to it real quick, I could have looked at this. I just want to try to get you into the headspace. I could have looked at this problem when we started out like this, and I could have said, okay, 4 and 24, what's the biggest number they have in common? Well, it's a 4, right? Okay, and then we have 4x's here and we have 3x's here. How many x's do both of these terms have? Well, they have 3x's, right? I could have pretty quickly realized, oh, a 4x cubed is what's coming out of both those terms. I could have done that in my head. And then from there, I could have asked myself the question, if I take a 4x cubed out of a 4x to the power of 4, what am I left with? Well, I'm just left with a single x, right? Okay, if I take a 4x cubed out of a 24x cubed, well, I'm taking all three x's out. I took a 4 out of a 24. You can think of it as like dividing it out or out of it. What am I left with? Well, I'm left with a 6 here, right? Right. And I could have actually gone straight to this if I, felt comfortable doing it. Notice, obviously they're the same answer. Okay. But this right here it's the longer way of doing it, but it is the foolproof way of doing it. Okay. So I just want you to know, if you're good at doing these in your head, I don't necessarily need to see these factor trees, but when things get complicated, sometimes it's good to just go back and use the factor trees. Okay, so let's try one of these examples. Let's go ahead and do this one in our head. Go ahead and copy this. We'll do it together. Okay, so we got a 9x to the power of 5 minus a 3x squared. All right, so I'm taking a look at these two numbers. By the way, this minus sign, we're not really worried about it just yet. We'll worry about it when we figure out what is left over after we get out the common factor. All right, so what is it? Well, a 9 and a 3, that's pretty obvious, right? I know I can take a 3 out of both of these numbers, all right? So the biggest number I can take out is a 3. When it comes to my variables, this one has 5x's, this has 2x's. How many x's can I take out of both of them? Well, 2, right? I can take 2 x's out of both of these terms. So I'm factoring out a 3x squared. Okay, so now here's the question. What's left over when I take a 3x squared out of both these terms? First thing, let's put that minus sign in between. Okay, and let's ask ourselves about this first term. If I take a 3 out of a 9, if I divide a 3 out of a 9, what's left over? Well, 3, right? If I take 2 x's out of 5 x's, how many am I left with? 3 x's, right? Okay, let's try with this. I took a 3x squared out of a 3x squared. Okay, think about that for a second. I took all of the numbers out and all of the variables out. Everything came out. So the question is what is left over if I take everything out? Okay, well, it's a 1. Okay, because if you think about it, if I were to go to multiply this, 3x squared times, this negative 1 would give me a negative 3x squared. Okay, so just remember, if you take everything out of a factor, what's left over is just that 1. Okay, it's not a 0, it's a dot that it disappears. There has to be something left over, and it's that 1. Okay, so there it is. We did that on our own in our head. If that was confusing, if you were like, I don't think I'm ready to do it, in my head right now, that is okay. Remember, you can do what we've done before, and you can break these down. I just want to show you how quickly it is. So, pretend we hadn't done that yet. Pretend we just broke these down. I know that 9 is 3 times 3. I know that we have 5 x's here, 2, 3, 4, 5. This 3, I can bring it, down. It can't be broken down, but it's part of the numbers I'm trying to find a common factor with. And this x squared is 2 x's, and I like to draw that line in between. Okay, so I would notice, okay, what do they have in common number-wise? They both have a 3. Okay, I would take the 3 out. What do they have in common variable-wise? Well, it looks like they both have 2 x's. I would take those 2 x's out. Okay, what's left of this term here? Well, it looks like a 3x cubed. Yep. What's left of this term? Nothing, right? Nothing. We took all numbers and variables out. So just remember, when that happens, that means a 1 would be left over. Okay, so this doesn't take that much longer. If you can't do it in your head, use the factor trees. It's really not that big of a deal. Okay, so I'm gonna have you guys go ahead and try out a couple of these on your own. I'm gonna have you guys factor these whichever way you feel comfortable. Okay, so if you need to use a factor tree, more power to you. If you can do it in your head, also more power to you. Okay, try them out. Okay, so taking a look at letter A, on both of these, I'm going to use factor trees just for the sake of covering everything. If you did it in your head, we should get the same answer. If we didn't, you might want to consider using some factor trees. Okay, so on letter A, breaking down this 2, it's already prime. I can only just bring it down. It looks like we have an x squared, which is 2 x's. Okay, 4 is 2 times 2. Those are prime, can't break them down anymore, and we got that x. Okay, so what do they have in common with one another? It looks like they both have a 2 and a single x. Okay, so that's my common factor I can bring out as a 2x. Okay, what's left over? Well, and by the way, I always like to write the parentheses, put that symbol in between, just so it's really easy. One of the common mistakes I see on this, by the way, is people just putting a single number in the parentheses. Just a single number. No, it needs to be what's left of both terms. All right, so that's why I like to do this first. Okay, so anyway, if I take a 2x out of a 2x squared, it looks like I'm left with an x. If I take a 2x out of a 4x, looks like I'm left with a 2. And there it is, it's factored. All right, just remember, we can check really quick to see if this is actually correct. Is 2x times x 2x squared? Yep. Is 2x times 2 4x? Yep. So we know it's factored. All right, taking a look at letter B. Let's do the same idea. 14 is a 2 times 7. Those are actually both prime. I can't break them down anymore. I have an x. Okay, put my line. 35 is a 3, or sorry, not a 3, a 5 times 7. All right, and it looks like I have a y here. All right, so everything's broken down. What do they have in common? Well, it looks like they both have a 7 in common. Okay, number-wise, variable-wise, what do they have in common? Nothing, right? This one doesn't have any x's. This one doesn't have any y's. So on this one, its common factor is just a 7. Okay, so just something to realize. You don't always take a variable out of both of them. Sometimes they don't have a variable in common. Sometimes they don't have a number in common. Okay, so it just really depends on the problem. Okay, so what's left over when I take a 7 out of a 14x? A 2x. Okay, got that minus sign. What's left when I take a 7 out of a 35y? Looks like a 5y. Okay, and there it is, just double checking. 7 times 2x is 14x. 7 times negative 5y is negative 35y. Yep, it's factored. Okay, so this is kind of an example of a problem. This might have been tricky to do in your head because it was a little different than the others. All right, so again, do what works best for you. I would say just when in doubt, use the factor trees. If you're like, I don't know, I wouldn't just try to guess or hope you get it right. But knowing how to do these in your head without using a factor tree is a very good skill that eventually I want everybody to get to the point of doing. Okay, but for now, do what works best for you. Okay, guys. So yeah, that's it for today. I'll see you.